Hello, so in this video we're going to look at something called connected particles. So these are two or more objects that we can essentially combine together as one. Okay, so I've got these two examples here. So this example here, we have a car towing some sort of weight right here, and we've got two objects here. So we've got the car and the weight, and they're being connected by some rope or some towing rope. Okay, and so what we're going to have here is what we mean by connected particle is two things. Firstly, we have the two or more objects connected together. Okay, so in this example with the car and the weight, they're connected together by this towing rope there in the middle. So they're connected together and they're traveling, so the objects are moving in the same direction. So again, in this example with the car and the weight attached to it, they're both going to move forwards, right? They're both going to move forwards. You can think of it like a car and a caravan, right? The caravan's being towed by the car, but they're both moving forward. So in this instance, when we've got two objects connected together and they're moving in the same direction, what we can effectively do, we can essentially combine these objects as one whole object into one. Okay, and this is what we call a connected particle. Okay, so a connected particle is basically when we can combine multiple objects or multiple particles into just one big object. Okay, and actually you'll see it simplifies problems down, because if we just consider one object, it's better than considering multiple different ones individually. Okay, and some forces we can kind of ignore and stuff like that. It'll make our working simpler. So that's what we're essentially going to be looking at, is looking at how we can combine multiple objects or together as one to make our workings a bit easier. Okay, now that's what we call the towing problem, where obviously we've got two objects being towed together by some rope. Now there's going to be two distinct problems in what we're going to look at in this video. Two distinct problems you need to be aware of. First one is the towing problem. So for example, a car towing a caravan. Okay, we're going to be looking at a bunch of examples like that. The next one is this. Now this is a lift, okay, or an elevator. So what's going on here? This is called the lift problem. What we're going to be considering is, well, we've got this elevator, right, this lift, this little square, right, being connected by rope. Okay, so everything's being connected again by this sort of rope. Okay, but we've got the lift, but inside we got another piece of weight. We've got another object, this black rectangle. That could be people inside the elevator, right? So we've got this whole elevator, but inside the elevator we've got, say, people, right? So we've got elevator and people, two distinct objects, if you will, and they're all being connected by this rope here. So again, this is another example of connected particles. Now what we'll be considering Newton's third law with this second type of problem here, Newton's third law. And so we've been looking at this sort of situation here about the various forces that occurs in this sort of problem, in this problem with the lift and the people inside. So what the various forces we're working with, and how we can use Newton's third law, which we'll look at as well, to study those forces, and so there we are. So we're going to look at these two distinct examples. Again, the video will be separated into those two, but yeah, we're going to look at the towing problem first. Okay, so we've got this problem first. Okay, so here we're told a lorry of mass m kilograms is towing a trailer of mass 3m kilograms along a straight horizontal road. The lorry and trailer are connected by a light inextensible tow bar. The lorry exerts a driving force of 50,000 newtons, causing the lorry and the trailer to accelerate at 5 meters per second. The lorry and the trailer experience resistances of 4,000 newtons and 10,000 newtons respectively. Okay, so there's a lot of stuff going on here. Now, for the first time looking at it, again, it's a bit scary. How do I put all this information down? What does all of it mean? Let's break it down. So, firstly, if we break it down, we're told that this lorry and trailer is on a straight horizontal road. Okay, so if I draw a nice horizontal line, like that, okay, so it's on some horizontal road like this. So we've got a lorry that's towing a trailer. So we've got this lorry, let's say it's here. So we've got a lorry and we've got a trailer over here. And they're being towed, okay, so the lorry is towing the trailer. So we've got some sort of towing line there, some sort of rope or something like that, some towing material that connects the two together. Okay, then I've got the masses. So the mass of the lorry is m. I don't know what it is, but it's m kilograms. The mass of the trailer is 3m kilograms. So 3m, not so kg. Okay, so that's the basic scenario. We've got the lorry connected by this towing thing by a trailer. Okay, now then we're told the lorry and the trailer are connected by a light inextensible tow bar. So again, this tow bar here. Now, light inextensible has a meaning. We'll look at that later on in the question. I'm not going to go into it now, but it is a modelling assumption you need to know. So we looked at modelling assumptions in the first chapter. We're going to be looking at what that means here. Okay. Then we're told the lorry exerts a driving force of 50,000 newtons. So a driving force from the lorry is going to pull it forward, and it's 50,000 newtons. Okay. So that's what driving force is. Remember, it's something that propels it forward. Okay. And there we are. And so this force causes the lorry and trailer to accelerate at 5 meters per second. So it's going to move forwards. So the acceleration forwards then is 5. Okay. There. Okay. So they both accelerate 5 meters per second forward. Okay. Then we're told finally the lorry and the trailer experience resistances of 4,000 and 10,000 newtons respectively. So the resistance, if it wants to move forward, the resistance is perhaps friction due to the road. It's going to go the other way, so it's going to go to the left. So firstly, the lorry has a resistance of 4,000 newtons. So actually, we're going to have a force. Where should I do it? Here. Okay, I'll do it down here. So we've got this force going to the left of 4,000 newtons. There we are. And likewise, the trailer also has a resistance of 10,000. So it's 10,000, push it that way. Okay, so hopefully with me there, that's all we're given. So hopefully you are comfortable having got to that diagram. It's going to be the same sort of diagram every single time. Now, the actual mechanics bit then, we need to find the mass of the lorry and hence the mass of the trailer. So we need to find what M here is essentially. Okay. Now, okay, so that's all the information. How do we begin to work this out? Now, I alluded to at the start that when we have two objects connected together, so we've got this tie rope, and they're moving in the same direction, that so they're both moving forward, we can consider them as just one particle. Now, there's one more thing you need to remember. There's another thing we need to consider that isn't explicitly told, and it's this tow rope here. It's this towing thing here. Now, you might see in part B. In part B, it's talking about tension in the tow bar. There's going to be a tension force in the bar itself. Okay. Now, I want you to imagine if you have some sort of rope here. If you pull the rope, if you try to pull the rope, if you try to extend or stretch a piece of rope out, what will happen is you got this force pulling. Again, we got I've drawn this little rope here. Think about tug of war, right? Think about tug of war. You got two. You got either end. So you got some people here. Let's say at either end of the rope. They're both pulling. They're both trying to stretch the rope out. Okay, from either side. Now, when a rope is being stretched or trying to be extended in some way, the rope or some string, there's going to be, obviously, you got the forces trying to pull out the rope. The rope's going to try and resist that. Now, as we discussed, the force in a rope is the tension. So what's going to happen is the tension is going to oppose the stretching. So if I divide this into two parts, right, the first half of the rope, obviously it's being stretched to the left. So there's going to be tension opposing that to the right, okay? And at the other end of the rope, pulled by this person here, is pulled to the right. There's going to be tension at that end of the rope going to the left, okay? So it's trying to resist any stretching, okay? So with that in mind, what's happening here with this tow rope is we've got the lorry, right, that's trying to move it, that's trying to stretch it forward, okay? And also we got this force here, resistance force, trying to pull the trailer to the left, okay? So you can see here, again, it's kind of like this tug of war situation. We've got the lorry, trying to push the rope one way, and the trailer trying to push the rope the other way. It's being stretched out, the tow bar, right? So again, what happens is that there's going to be a tension here from the lorry. So again, if I split this into two, we've got a tension from the lorry in the rope. So the tension by the lorry is going to go to the left because the lorry is trying to pull the tow bar to the right. So the tension is going to go to the left to oppose the stretching due to the lorry. Okay, on the left side of the tow bar, so the rope, well, the trailer is going to want to push it to the left, and it's going to stretch out the tow bar again. So the tow bar is going to go to the right. Okay, so the tension in the tow bar is going to go to the right to oppose the trailer pushing it to the left to stretch it out. Okay, so that there's tension either side of the rope here, and again, that will always be the case. So hopefully you understand. Hopefully this analogy of the tug of war, at either end, the rope is being stretched out either end. The tension has to be the opposite either side to oppose the stretching force. Okay, so there we are. So that is the full, actually complete diagram. Okay, obviously we could also include mass, the weight, sorry, if you wanted to. So each side has weight as well. I'm not going to include that here unless we really need it, because we might not need it. Okay, now, okay, so that's all the forces we actually need to consider. Now, to find the mass then, so we've established there's tension either side of the rope, so the side by the trailer and the side by the lorry. Hopefully, again, you're comfortable with why the tension is to the right by the trailer and to the left by the lorry, because it's opposing the stretching. Okay, right, so what we can do is, as I alluded to, we can consider, because the lorry and the trailer are connected together, they can be considered as one object. Now what we can do here is, if we were to consider it as one object, what we can do is firstly just add the masses together. So the total mass, that's going to be what? 3m add m kg, which is 4m kg. Okay, so the mass of the lorry added the mass of the trailer. So that's going to be the total mass of this one total object. So I'm basically just combining them into one. Now, I also need to combine the forces acting on both of them together. So if I then, because it's accelerating to the right, it's moving to the right, let's resolve to the right. Okay, so firstly, if we consider the lorry, the force that's acting to the right of it is this 50,000 newtons, okay? If I then, that's the only force moving to the right from the lorry. What about the trailer? Okay, now, we've got this 10,000 newtons going to the left, right? So it's not going to the right, to the left. But we've got the tension at the first half of the rope. That's pulling the trailer forward, okay? So actually we need to add on the tension, okay? So what we're doing is basically finding all the right forces, the forces to the right, of both the trailer and the lorry. Then we're going to take away all the left forces, so the opposite direction. Well, for the lorry, we've actually got the tension on the other end of the rope, pulling it to the left. So I'm going to take away T, and then we're going to take away 4,000, which is this resistance here, okay? So take away T, take away 4,000. And then we also got this 10,000 resistance from the trailer to the left as well. So take away 10,000. And then that equals mass times acceleration, right? That equals MA. Now the mass is the total mass, because we're considering it together, which is 4M. So 4M times the acceleration. The acceleration is 5. And there we are. So at that point we get this equation here. Okay, and if I simplify this equation, well, if I do 50,000, take away 4,000, take away 10,000, I get 36,000. Then have plus T, take away T. Well, they cancel each other out. The tensions here cancel. So then I just get 36,000 is 20M. And you can see why we want to consider the object as a whole, because the tensions go away. So I don't need to find out the individual tension at each half of the rope. So it makes the problem easy, because now I can just work out M by solving this equation. So if I divide by 20, I get about 1,800, okay? And so there we are. Then it wants me to work out the mass of the lorry and the mass of the trailer. Well, firstly, the lorry is M. It's M kilograms. So actually, that is the mass of the lorry. So it's 1,800 kilograms. Again, remember, always in kilograms. It's our SI, our standard unit for weight, for mass. Okay, and the mass of the trailer, well, it's 3M, so we need to triple it, right? Times by 3. If we do that, we get 5,400 kilograms. And there we are. Those are the masses of the lorry and the trailer. Okay, and so in part B, now it does want me to find the tension in the tow bar. There's no getting away from that now. We need to find the tension at either half of the rope, at either end of the rope. Okay, so how are we going to do that? Well, in part A, we considered the whole of the two objects as one. So the lorry and the trailer combined. This is what we call the whole system. Okay, so essentially we considered the system of the lorry and the trailer together. So the whole system as one. What we're going to do to work out the tension is now not combine them together, but actually consider them separately. So if I consider, say, the lorry separately, so the lorry and its forces on its own, okay, so now if I just consider the lorry, I might be able to work out the tension. So again, we've got the lorry here. So the lorry, what's the mass of the lorry? Well, we worked that out in part A. It was 1,800 kilograms. Okay, and the forces on the lorry, well, it's being pulled forward by 50,000. And it's being pulled back well, by two forces actually. Firstly, the tension that's pulling it backwards in the rope, and also this other resistance force of 4,000 newtons, okay? Perhaps due to friction or something like that, right? So that's the whole system we're dealing with, and it's accelerating forwards by 5, okay? So what we can do here is to work out tension. Well, again, we can consider resolving, right? If I resolve forwards, well, firstly, the forwards force is 50,000. Take away the backwards forces, so the opposite way. So take away the tension, that's going backwards. Take away the 4,000, that's also going backwards. That's my overall force. So overall, this equals mass times acceleration, where the mass is 1800 times the acceleration of 5. Now it should be quite clear how we can work out t by solving this equation. So if I do 50,000, take away 4,000, I get 4,600. 46,000, take away t, equals, what, 1,800 times 5 is 9,000. Then I can just solve the t. So if I take away 9,000 from 4,600, I get 37,000. So that is my tension there. Okay. Alternatively, I didn't have to consider the lorry. I could have considered the other object instead. So what about the trailer? Again, okay, so if I do the trailer, I'm allowed to do that. And actually it might be a bit more simple. There's less forces on it. So we've got a trailer. Again, the mass of the trailer, well, it was 5,400, right? That's what we worked out. That is 3M. Okay, so it's been, firstly, it's been pulled, the trailer is pulled forward by this tension force at the other end of the rope, so T, and it's being pulled back by this force of 10,000. And again, it's accelerating forwards by 5. Now, if we were to resolve forwards, for the trailer here, well, the forwards force is T, take away the backwards force of 10,000, equals mass times acceleration. So it's 5,400 times the acceleration of 5. And again, I can alternatively then just find T by solving this equation. So T take away 10,000 equals 27,000. And again, hopefully then you'll see that T is going to be 37,000 as well. So the tensions are the same in no matter what object you consider, okay? But there we are, we can work out tension. So again, there's this problem here, this sort of towing problem where two things are towed together. It's pretty much the same thing every time. The same sort of method are done here. You can consider it as a whole by combining the masses and combining the forces. But also maybe you need to consider them separately as well as individual objects. And so there we are. That's the premise. Now in part C, it says explain how the modelling assumptions that the tow bar is light and inextensible affects your answer. So what does light and inextensible mean? Well, where do I have room? I don't know. Okay, so firstly, light. Now again, these two are modelling assumptions you need to know, but that we looked at in the first chapter. But this is where it's applied, okay? So firstly, the light tow bar or the light rope or something like that, or a light string. Light means no mass. So that means the rope itself, if I go back to my diagram, the rope itself isn't weighing the lorry or the trailer down. So it's not affecting its movement in any way. So there's no mass coming from the tow bar. But also, in addition, the tension is the same throughout the rope or throughout the tow bar. That's what a light rope or a light string or a light tow bar, that's what light means in this context, okay? So it has no mass, but also the tension is the same throughout the tow bar. We saw that here. The tension, obviously, the tension at either part, at either end of the rope is opposite, because at one end, so here, the tension is going to the left, because the lorry is stretching it to the right, so it's opposing the stretching, as we discussed. But the trailer, the tension's going the other way to the right, because the trailer wants to move to the left. So again, it's being stretched the other end. But despite going opposite directions, the tension physically is the same number, as we saw, right? It was 37,000. Now again, that might seem a bit counterintuitive, because you think, well, the trailer is far heavier than the lorry. So if you think back to this tug-of-war situation, you'd maybe think the tension would be heavier on the left side with the heavier mass, but not in this case. The tension is equal throughout the tow bar, okay, despite anything else. That's what light means, okay. Now, inextensible, that means that the acceleration of both objects, so here the lorry and the trailer, are the same. So the objects connected by the tow bar, so the lorry and the trailer, they both travel at the same acceleration. Now, I guess a question you might have thought of, well, again, if the acceleration is 5, so if I bring that down here, so the acceleration is 5, that's the acceleration for both the lorry and the trailer, right? You might be thinking, well, aren't they different? Maybe the lorry, again, the lorry is, the trailer is heavier than the lorry, but you might be thinking, well, the acceleration might be different, right? But again, not necessarily, because we added this assumption, which again simplifies our calculations. So the acceleration of both the trailer and the lorry are both 5, and they're both moving forwards, okay? That's what an inextensible rope does. So if, again, two objects are connected by the same rope or the tow bar, the acceleration of both objects connected have to be the same, okay? And that's what that means, okay? So there we are. And again, you do need to remember what those assumptions mean, and that's what I just said here, okay? Right. Okay, so we've got this question here. So now we're told two particles, P and Q, of masses 5 kilograms and 3 kilograms connected by a light and extensible string. Particle P is pulled by horizontal force, magnitude 40, along a rough horizontal plane. Particle P experiences a friction of 10 newtons and particle Q experiences a friction of 6. It wants me to find the acceleration, okay? So again, I'm just going to plot the information down and you'll spot it's basically exactly the same scenario. So firstly, we've got these particles P and Q. So again, the objects, you can think of it as a car and a trailer like last time. But it's on a rough horizontal plane, horizontal. So again, it's a horizontal like this. And we got P and Q. So if I say P is here, and then Q is here, and we're told they're connected by a light inextensible string. So we've got this string here, kind of like the tow bar again, right? And then we're told that particle P is pulled by a horizontal force of 40, so pulled there by 40, okay? And we're also told that particle P experiences a friction of 10. So there's going to be, if I draw this a bit differently here, so 10 newtons is going to be there. That's the friction from P and the surface. And Q also has friction of 6. So it's going to be 6 there. Okay, opposing, it's going to go forward, right? It's going to go forwards, but friction will go the other way to oppose it. There we are. And so talking about acceleration, well, it's going to be acceleration, so that's what I want to work out. So now I'm going to say it's A, meters per second, that's the acceleration A. I don't know what it is, but I'm just going to call it A. Now, again, the masses, I should have added masses on, the masses, but P is 5, the 5 kilograms, and Q is 3 kilograms. There we are. What else are we missing? The tension. The tension. Well, again, if I split it in half, well, again, at one end, you got P that's pulling the string forwards, stretching it forwards, so the tension is going to go the other way to oppose it. And then Q, well, Q is going to want to move backwards because of the friction slowing it down. So again, it's stretching backwards at the other end, so the tension's going to go forwards there. So we've got two tensions at either end there. Okay, and again, it's light. The string is light. Where was it? Light, which means the tension is the same at either end. And it's inextensible, which means the acceleration is the same in both particles. So A for both P and Q. Okay, that's the acceleration. Okay, so how are we going to find the acceleration? Okay, well, what we can do is consider it as a whole. So if I consider it as a whole, so a whole system. Okay, well, firstly, if I do F equals ma, right? Well, firstly, if we're considering the whole system, so P and Q put together, well, what are the forces put together? Well, we've got, so if we resolve forwards, well, the forwards forces, well, this is 40 going forwards. Then we've got this tension at Q, so add T, and that's really it. Then I'm going to take away the left forces the other way. So we've got this other tension going to the left. That's coming from P. Take away this 10 newtons. And also this 6 newtons going that way as well. Okay, so that's all the backwards forces. That's the overall. So that equals mass times acceleration. Well, the mass, if it's combined together, that means we need to add the masses. So 3 and 5 is 8. So 8 times the acceleration, which is A. So 8A. Well, again, the beauty here is the T's cancel, so we don't need to consider tension here. So, okay. If we simplify this then, well, 14 minus 10 minus 6 is 24. That equals 8A. Therefore, A is 24 over 8, which is 3. And there we are. So 3 for the acceleration of both. There. And there we are, that's the acceleration. And then in part B, it wants to find the tension in the string. The tension. Okay. Right, so if I was to then consider one of the particles, let's say Q. Let's say Q. There's less going on at Q, right? Again, likewise with the last example, you can pick either particle, but you need to consider separately. So particle Q here, which is 3 kilograms, is being pulled forwards by tension here, and it's going backwards by 6 here. So if I do F equals ma on this Q, well, if I resolve forwards then, and again it's accelerating at 3, right, that's what we worked out, the acceleration. If I resolve forwards, well, then the forwards force is T, take away 6 newtons. That's going to equal mass times acceleration. So 3 times 3. So therefore T minus 6 is 9. Therefore T is going to be 15 newtons there. So that's my tension. Okay. What I'm going to say is we could do all this alternatively. Okay, there's an alternative method to work out the acceleration and the acceleration and the tension. And alternatively, the alternative is, what if we just don't consider the whole system? What if we don't consider combining them? What if we just considered the objects separately? You can solve it that way as well. It just takes longer. So if we were to pick. So if we were to just consider P and Q separately, by P, well, again, P is 5 kilograms. And then the forces acting on P, well, it's forwards by 40. And it's being pulled back by the tension and the resistance of 10 newtons, okay? And it's accelerating. Well, at this point, let's say I want to work out the acceleration in a different way. Again, that's just A, okay? And then if I consider Q, well, again, Q is 3 kilograms, is being pulled forward by the tension and backwards by 6 newtons. Again, accelerating at A. Now, what I could do instead is, if I consider the two objects separately, the two particles separately, I get two different equations. So if I resolve forwards in both of them, well, firstly, for P, forwards is 40, take away the two backwards forces, so take away T, take away 10 equals MA, so 5 lots of A. So then 30 take away T is 5A. But the problem here is, this is why I wanted to consider doing it as a whole, because the T goes away. But if you do it separately, so consider the particles separately, you get an equation with A and T. So you can't solve A for A right away. Okay, if I did the same for Q then, so if I resolve forwards, well, that's going to be T, take away 6, equals MA, so 3 times A. And again, I get the same situation. I've got this equation here of T take away 6 is 3A. But actually, we can solve for A and T. I can solve for the acceleration and the tension because these are simultaneous equations. So what you'd end up with instead is, if you consider them separately, you get simultaneous equations. So it takes a little bit longer, but it's still perfectly solvable, okay? And so at that point, if you do solve them, I'm not going to do it here, so we solve them simultaneously, you should get A equals 3 and the tension equals 15, okay, like what we got in part A and part B, okay. But yeah, I'll leave you with that. Okay, then part C. Part C then, it says, explain how the modelling assumptions that the string, so they've been connecting the two things, is light and inextensible. How has that been used? Well, as we just discussed, light means the string has no mass and tension is the same throughout the string. And it's inextensible, which means the acceleration of both objects, so both P and Q, are the same. Okay, and there we are. Okay, so let's have a look at this question here. Now this scenario is a bit different. So what's going on here is, before we look at the question itself, I want to go over this as well. So what we've looked at so far is, again, this sort of so we've got two objects. Actually, no. So what we looked at so far is the string or the tow bar connecting the two things, so the car and the trailer. What we looked at so far is the string being stretched apart. Okay, so for example, again, like tug of war. Again, let's say we've got this person to the right that's pulling it to the right, and the person on the left pulling it to the left. This is my string. Now, if I split this into half, right? So if I split the string into two parts, or two parts, well, at either end, again, at one end it's being pushed, it's been stretched to the left, so the tension is going to go to the right, and again on the other end it's been stretched to the right, so it's going to go to the left. It's opposing the stretching. Okay, what I want to look at now is, instead of stretching, what if we compress or squash down on the string or the spring or whatever it is. Okay, and in this example you can see just that. You got this hand that's pulling, that's trying to push or squash down this spring or string. Okay, it's being squashed or compressed down. Okay, so the hand on the top is squashing it from the top, and the hand on the bottom is squashing it from the bottom. Okay, in this way. So those are the forces of the hand pulling it down and squashing it down. So it's not being extended here. Okay, it's not being extended, it's being crushed down. So what happens now is, there's not a tension force being created. There is still a force, but the force is again going to oppose the squashing. So if I again split this little spring here into two halves, Well, the one end, well, if we look at it from on the top half, well, this hand here is squashing it down like this. So to oppose the spring being squashed down, the spring, the force in the spring will push, will have a force going upwards. This is not tension, it's called thrust, okay? Likewise, the hand on the bottom is trying to push or squeeze down the spring up. So if the hand is trying to squish the spring up, at that end, the spring is going to create a downwards force, which is again thrust, okay? So thrust is when we're squashing down and condensing or compressing a string or spring or anything like that, rather than being stretched out, okay? And so that's thrust, okay? So again, the idea is just the force in the string or whatever is trying to oppose what the motion happening to it. So if it wants to stretch, it's going to oppose the stretching, or it's going to oppose the compression. Okay, so hopefully with me there. So there we are. So what we're going to look at are some examples where instead of being stretched, like in the first two examples, being stretched out, it's now going to be squashed in. Okay, so let's have a look at this example here. So we're told two particles P and Q of mass is 20 kilograms and n kilograms are connected by a light and extensible rod. Okay, rod again is like a plank of wood, sort of material which doesn't bend at all. Okay, kind of like a seesaw. Like so, a seesaw goes up and down, but you can't bend a seesaw. Right, it's really, really stiff. Anyway, so if I draw this out then, well, firstly, we've got a smooth horizontal plane. So a horizontal like this. So we have particles P and Q. So let's say Q is here and P is here. And they're being connected by this light inextensible rod. So again, the rod connects it together. It's like a tow bar, essentially, right? It's the same sort of idea, just with different words, okay? The mass of P is 20, so 20 kilograms here, and the mass of Q is M. There we are. Okay, then in terms of forces, what we're told is a horizontal force of 60 newtons is applied to Q in a direction towards P. Okay, so if it's going towards P, it's going to want to move to the right. Okay, so the force is pushing Q to the right like this. That's in the direction of P. Okay, and we're told it's 60. Okay, and then it says it causes the particle to accelerate, to move with acceleration 2. So it's going to want to move to the right. Okay, if it's being pushed to the right. So the acceleration is 2. And again, it's going to be either way. Okay, right. Now, again, you might be thinking, well, there's going to be tension, right? But it's not tension. That's why I went over this example. It's not tension here. Why? Because the actual tow bar, or the rod, or whatever they want to call it, the thing connecting it, this sort of rope thingy here, the rod, what's connecting it, is not being stretched out, okay? Because what's happening is Q is not going, it's not trying to pull away from the tow bar. This force here is pushing it into the tow bar, okay? So it's going the opposite way to what we've seen so far. So this force here is pushing it towards the tow bar. So again, it's having this effect where it's being squashed into the tow bar. So to oppose the squashing by this force pushing Q into the tow bar is going to go and counteract that and say, no, I'm going to resist you pushing into me. So I'm going to create a thrust force. So I'm going to say T and thrust here. To distinguish, I'm using T because it stands for thrust, not tension here. Okay, and it's going to be the same the other way. Okay, so T is going to go that way as well. So the thrust is going to be there as well. Okay, and that thrust is pushing P forward as well. So there we are. Okay, so that's the situation here. So now we got thrust, not tension, because it's been because Q again is being pushed into the tow bar. It's being pushed into it. The thrust wants to kind of push it back out to oppose the squashing. Okay, so hopefully it made sense. So it's thrust, and you can see in part B he wants to find thrust, not tension here. Okay, so again, hopefully with me there. Okay, so there we are. So part A, it wants me to find the mass of Q. So what does M mean? Again, okay, so if I just consider the whole system again here. Okay, well, if I then resolve forwards, because it's going to move forwards, right? Well, what's the force going forwards? Well, we've got this 60 newtons. Now that's going forwards, remember? So that's forwards. So 60. And then we've got this thrust force going forwards. So add T thrust. And then what about the forces going the other way? What about the forces going to the left? Well, actually, we've got this thrust force as well going the other way. And that has to equal mass times acceleration. But if we're considering the whole thing, we add the masses together. So we have 20 add M. Okay, that's 20 from P and M from Q. So we add them together times the acceleration, which is 2. Okay, well, the thrust forces here cancel. So we're just left with 60 equals 2 lots of 20 add M. So at that point, we solve for M. If we expand the brackets, we get 40 add 2M. And so then we get 20 is 2M, therefore M is 10 kilograms. So that is the mass of Q. Okay, I can add that on now. 10 here. Okay, then it wants me to find the thrust in the rod. So at that point, the thrust in the rod, I can then, I'm going to need to consider P or Q separately. So if I let's consider just P, right? Only has one force on, quite easy, right? So P, mass of 20. Now, the acceleration is again 2 forwards, and Q and P is being pushed by the thrust in the thing, in the rod, in the tow rope thing, whatever we want to call it. So we have the thrust force pushing it forward there. Okay. And so if we use F equals ma, if we resolve forwards then, well, the only force that's forwards is the thrust, right? Then that equals mass times acceleration. Well, it's 20 for the mass times 2. So the thrust is 40 newtons there. Okay. And there we are. Okay, so we've got this question here, which is a bit trickier, a trickier question, and it will involve linking the idea of thrust. So what happens when the tow bar connects, so the rope connecting the two things? What happens when the objects are squashed into the tow bar? Okay, so let's have a look at this question. Now I'm not going to read it out. I'm just going to again just jump right into sketching this, the information given. So we're told it's on a horizontal road. Great, horizontal. We're also told we've got a car connected to a trailer. So if we have the car here and the trailer here, well, the car has mass 900. The trailer has mass 300. And then what about the forces? And well, it's being connected, right? First of all, it's being connected by this little rope here, the tow bar. And again, there's going to be actually, let's just read. Well, firstly, in terms of forces, we're told the resistances to the motion. Well, the resistance to the car is 200, so it's going to be 200 that way. And the trailer has a resistance of 100 newtons. Okay, again, it could be due to friction on the road or something like that. The engine of the car produces a constant driving force of 1200 newtons. So the driving force will go forwards of 1200 newtons. Okay, then we're also told, we're told it's a rope, a tow bar, but that means if it's being pushed forwards now, so if the car is moving forwards, so the acceleration is forwards, it's going to be stretched, okay? This tow bar is being stretched forwards, so the tension is going to oppose the stretching to the right, so it's going to go to the left. Okay, likewise, the trailer is also pushing out the rope. It's going to push it to the left, kind of like a tug of war situation. So the tension is going to go to the right to oppose the stretching. Okay, at either end. There we are. Now, then it's just a standard sort of problem we've seen in the last few examples. So we need to find the acceleration and the tension T. Okay, pretty classic examples. So again, if I just consider the whole system then firstly, or again, alternatively, you could consider separately the car and the trailer, then you'd end up with simultaneous equations. Okay, you could pick however you want, but if we do the whole system, then if we use F equals ma, if we resolve forwards then, because that's where the motion is, going forwards, the forwards forces are 1200 here, then this tension here, take away then the backward forces, so again we've got the tension backwards here at this end, then we've got 200 newtons there, and then 100 newtons here, and that equals ma. Well, if it's the whole system, so we combine the masses, so 300 add 900 is 1200 times the acceleration a. Okay, if we simplify this equation, we get (900) equals 1200 a. So therefore a, if we divide by 1200, we get 0.75 meters per second. And hang on, there we are. We've shown that the acceleration is 0.75. Great, so we're on the right track. Then it wants me to find the magnitude of the tension. So again, magnitude is just the physical length of it, the size of it. Okay, so if I want to find the tension, I'm going to need to start considering separately, so either the car or the trailer. Well, if I pick the trailer, again, you can pick whatever you want, it doesn't matter. So the trailer again has a mass of 300 kilograms, has a tension force going forward and the resistance of 100 newtons going backwards. Yes, so if we resolve forces here, so if we resolve forwards, again it's accelerating forwards. Well, we worked out the acceleration, it's 0.75. So the forwards force is T, take away 100 newtons, that's going to equal ma, so 300 lots of 0.75. So at that point we can solve for T, so T take away 100 is 225, so if I add 100, T is 325, and there we are. Okay, part C, this is where it gets interesting. So now we're told the car is moving along the road. When the driver sees a set of traffic lights that have turned red, he reduces the force produced by the engine to 0. This force here, the driving force, because of the engine, that goes to 0. So there is no driving force forward, okay? And he applies the brakes. The brakes produce a force on the car of magnitude F newtons, and the trailer decelerates. Okay, so if I just draw what's happening here then, so it's a very slightly different scenario. So what's happened is, again, we've got the road, we have our car, which is 900 kilograms. We have the trailer of 300 kilograms. And here, what we're told is there's no driving force. This force goes to 0. So there is no force forward from the car. What we're also told is the brakes produced a force F newtons. So if you think about it, the brakes will try and slow you down. So the brake will have a braking force acting the other way. So I'll call that B. Okay, B for the braking force. Again, they're all... actually, I'm going to draw the blocks a bit larger because there's going to be a lot of forces here. There we are. Trailer, 300 kilograms. Then we have the car, 900. So again, they're being connected by rope. But there's a braking force here of B. That's the braking force. That's when the car slams on the brakes. So a brake obviously slows you down. So there we are. We're told it's F. Okay, we're told it's F. Okay, not B, but F. And what we're also told is the resistances to motion are unchanged, and the magnitude of the thrust is 100 newtons. Work out the value of F. Okay, so everything else is the same. So again, there's going to be this tow bar here. There's all. We're also going to have this resistance force of 200, slowing the car down. Again, that could be due to friction. The trailer, well, the trailer has a force of 100 resisting it. And there we are. Now, the force is here. We no longer have tension. Okay, there's no tension, so it's not this way. Think about it now. It's the car kind of is slowing down. It's kind of being pushed to the left. Okay, there are no forces on the car now that's pushing it to the right. It's all to the left. So what's effectively happening now is, again, the car is being squashed into. If it's being pushed to the left, it's being pushed into the tow bar. So now it's not the tow bar isn't being stretched, but it's being squashed down. So it's being squashed. So on this side, if the car is moving to the left, the rope has a tension to the right of the car. Okay, and this is your thrust. Okay, it's been squashed into it. The car's been pressed into the rope, into the tow bar. Likewise, the trailer will then have a thrust here as well. There. Okay. And the thrusters will be opposite directions at either end. Okay. But there we are. Now, that's all the forces then. So we don't have tension anymore, we have the thrust. Hopefully that made sense. Okay, why we have thrust here. Okay, so the resistance, that's all of it. We're also told it's 100. Okay, so actually we know that the thrust is actually 100. So we can say 100 here. 100. And there we are. Now, as for acceleration, now we can still say you can put acceleration wherever you want. Okay, acceleration. The acceleration would be different, obviously, because the forces have changed. I'll call that A. Okay. Right. So it wants me to find F here. So if I start to resolve, well, what could we do here? Well, again, if I perhaps consider resolving as a whole system again. So if I resolve, if I'm taking the acceleration as forwards, maybe let's go forwards, okay? Well, the only forwards force is the thrust here, 100. But then all the other forces are backwards. So I'm going to take away the other 100, take away the 100 here. Take away these two forces, so take away F, take away 200. And then that's going to equal MA. So mass times acceleration. Well, again, the whole system, we need to add the masses. So 1200 times A. Now, if I simplify this, well, I'm going to get Minus 300 minus F is 12,000 A. And so you can start to see the problem here. The problem is we have F and A. Okay, again, to emphasize, the acceleration is different now because the forces have changed. So we can't find F without finding A first. So the whole system isn't sufficient on its own. So now we need to consider an object separately. Let's take the trailer. Okay, let's take the trailer. If we then resolve forwards with the trailer, there are no forwards forces. It's only going backwards by this force of 100, so it's going to be 0 because there's no forward force. Take away the 100 here, take away the other 100 here. So then we're going to get MA, so mass of 300 times A. So if I do that, then minus 200 equals 300A. Therefore, A is minus 200 over 300. That's minus 2/3. And so the acceleration is negative. Now don't freak out, that makes perfect sense, because remember, negative acceleration means it's just slowing down. Right, so you know what's going on, right? The car is braking, so the whole thing is slowing down. So so it's slowing down, so it's minus 2/3 here. Okay, that's the acceleration. Now that's the acceleration, right? So now I can work out F. So then what I'm going to do now is sub A into that equation. So the equation is minus 300 minus F is equal to 1200A. So therefore minus 300 minus F is 1200, lots of minus 2/3. So if I work that out, minus 800. So therefore F, if I add 800 to both sides, I get 500 newtons. And there we are. Okay, so that's the braking force there. Cool. So that's that question. Again, quite hard, especially that final part of the question, but hopefully they made sense with the forces, in particular the thrust, okay, that we've got going on there. Right. Okay, so we've got this question here. Now, again, there's something else to consider, but ever so slightly different, but let's just get to it. So let's have a look at this question here. So we're told here a car is towing a trailer along a straight horizontal road. So again, we got this horizontal. We have a car towing a trailer. So let's say we have the car here. So the car is 1400 kilograms. The trailer is 700 kilograms. Okay. And it's being connected by a tow rope. Okay. The car and the trailer are models of particles. Okay, blah, blah, blah. The resistance to motion of the car is 630 newtons. So there's a resistance that way of 630. Again, you can think of it like friction maybe. And the trailer has resistance of 280. And so again, the motion is accelerating forwards. It's moving forwards. So that means there's tension, because if it's moving forwards, it's being driven forward. The rope is being stretched. Okay, the car wants to move forwards, so it's going to stretch out the rope. Okay, so the tension on that end is going to be that to the left, and at the trailer end, it's going to be to the right. So that's all my forces. Now, again, he wants the acceleration and the tension. Okay, pretty standard by now. So again, if we consider firstly the whole thing, so combine them as one. So firstly, F equals ma. If we resolve, say forwards, then the forward forces. Oh, are we not told a forward force for the car? Yes, sorry, the driving force is 2,380. There we are. That's pushing the car forward. Okay, so that's the forward force. And then we've got the tension forwards here, and that's really it. Then take away the backward forces, so again take away the other tension at the other end here, take away 630, take away 280, that equals MA. Well, the total mass is 2100 times the acceleration, which is A. So there we are. Okay. So if we simplify this, well, we get at the we get 1470 1470 equals 2100A. So if we divide by 2100, that would get me the acceleration to be at 0.7 meters per second. So 0.7 there. So that's my acceleration. 0.7. Cool. Then it wants the tension here. So if I now just pick, let's say, the trailer on its own now. Well, firstly, again, if we resolve forwards, well, the forward force is the tension for the trailer. Take away the backward force on the trailer, which is 280. Again, that equals MA. Well, the mass is 700. Lots of A, which is 0.7. That's the acceleration. Okay, so we get T minus 280 is 490. And so therefore the tension, if we add 280 on, we get 770 newtons. There we are. Cool. Now part C, this is where things get interesting, and this is the point I want to raise as well. Okay, when the car and the trailer is moving at speed 12 meters per second, the tow rope breaks. The tow bar connecting them, it breaks. Assuming that the driving force on the car and the resistance to motion are unchanged, work out the distance 4 seconds after the tow rope breaks. Again, it's going to involve SUVAT, hence I've got the SUVAT equation here, because it's talking about distance, time and speed. Okay, we can only work that out using SUVAT. Okay, but the interesting scenario is the tow rope is broken. If I now redraw this situation, there is no tow rope here now, okay? So we have our car again, which is, I don't know what the mass is, I forgot. Then we got the trailer. Now, what we're told is, the driving force and the resistance forces are unchanged. So the driving force here is still 2,380. The resistance to the car is still 630. And the trailer still has a resistance of 280. Now, the tow rope breaks. It breaks. So there is no tow rope, so there's no tension. So actually, it does make things easier. So if you're in a situation where you're told, and I've highlighted it here, when you got the string or the tow rope connecting the two objects, if that breaks or if it becomes slack, we'll see more about that in the next video, the string basically disintegrates and there's no tension, there's no force in the string anymore, so there's no tension when it breaks or becomes slack, as we call it. Okay, so what it's asking is, we're told that the trailer, they're moving at the speed of 12. So if I list that on, the speed is 12 meters per second. Now, as for the acceleration is not 0.7 anymore because the forces have changed. There's no longer any tension. Okay, so the acceleration is going to be different. Okay, and there we are. And then we're told to find the distance the car moves after 4 seconds after it brakes. So let's say again it starts with speed 12. Let's say the car again it starts here. What about after 4 seconds? Let's say after 4 seconds it ends up here somewhere. If the time is 4 seconds, what's the distance going to be? That's going to involve SUVAT, right? Okay, so again, if I list my SUVAT, so S, that's my distance, that's what I'm going to work out. U, the initial speed is 12. V, I don't know anything about the final speed after 4 seconds. I don't really care about it. A, now A is just A. I don't know what the acceleration is, but T is 4. Now, you can see I'm going to need to work out the acceleration. Okay, I can't work out the final speed. I don't have the information for that, but I can work out the acceleration using F equals ma in this situation here. So before I use SUVAT, I actually need to work out the acceleration. I'm going to do that here. So how can I work out acceleration? Again, let's consider the, well, we don't have a whole system anymore, do we? Because the objects aren't connected. The car and the trailer no longer have a rope connecting them. So we cannot consider them as a whole. We can only consider, say, the car separately. Okay, we cannot and must not combine them. They're not connected. So if I do it down here, so let's say with the car, if I redraw what we've got now, so we got the car was 900 kilograms, I think. Oh no, 1400 kilograms. There we are. And again, it's being pulled forward by the driving force of 2,380 and a resistance of 630 and the acceleration A forwards. Okay, so if we do F equals ma, well, if we resolve forwards, well, that's 2,380, take away the 630 equals mass 1400 times A. So we can work out A here. So if we simplify that, we get 1750 equals 1400 A. Therefore A is, if we divide by 1400, we get the new acceleration to be 1.25 there. Okay, and so indeed you can confirm to yourself that the acceleration is now different because the forces have changed. Okay, so the new acceleration in this case, once the tow bar brakes, is now 1.25. And actually, that is now A. We can use A as 1.25 in my SUVAT. So now at that point, we're just applying SUVAT. So I want the formula that excludes V. So if I go back to my SUVAT list, it's this formula here. S is UT add a half AT squared. So that means S is going to be 12 lots of 4 add a half lots of 1.25 lots of 4 all squared. And that will get me 58 meters there, and that is my distance. So 58 meters. Then in part D, it says state how you use the modelling assumption that the tow rope is inextensible. So again, we looked at this before, so you need to remember inextensible means the acceleration of the car and the trailer are the same. So the objects connected by the rope, if it's inextensible, the acceleration of both objects are the same. So we're going to finish off with some exam questions. So again, we're just going to finish off, just practice what we've learned with these questions. So again, we got this car that's towing a trailer here. They've kind of kindly drawn a bit of it for us actually. So we're told stuff about the forces. So the resistance to motion of the car. So it's going to, if it's so it's going to resist, so it's going to go backwards. And we're told it's 2R, okay? 2R there. There we are. So that's the resistance of the car. The resistance of the trailer is R, so it's going to go back by R here. And the rope is light and inextensible, okay, as usual. The acceleration is A, so again it's going to accelerate forwards. And the driving force of the engine of the car is 7,400, so it's been pulled forward by 7,400 newtons. So it's all moving forward, it's accelerating forwards. Okay, and we're also told the tension in the tow rope is 2,400. So again, we've got the rope is being stretched to the right and to the left either end. So the tension at the end of the car is T that way. Well, we know the tension is 2,400 that way. And also that way of 2,400 as well. Okay. So there we are. Then we need to find the acceleration A. So, okay. You might be thinking, well, let's just consider the whole system, right? If we did that, you can do that. It is connected. They're connected by the rope, and they're all moving in the trailer and the car are moving in the same direction. So if we resolve forwards, then, well, the forward forces are 7,400. Take away 2R. We got this 2,400 forward. Then we take away the 2R going backwards. Take away the other 2,400 of the tension. Take away the R by the trailer. Okay, so that's all the forward forces. Take away by the left forces, the backward forces. That has to equal MA. So the total mass is, well, add the masses together. 1,200 add 400 is 1,600 times the acceleration A. So if I simplify this equation, then I'm going to get I'm going to get 7,400 take away 3 lots of R equals 1,600A. Now the problem is I can't work out acceleration here because I need to work out what this R is as well. So actually it's not enough to just consider the whole system. I now need to consider separately either the car or the trailer. Let's consider the trailer, okay? So if I just consider the trailer then, so now if I resolve forwards, well, the only forward force on the trailer is this tension of 2,400. Take away R going backwards equals MA, but the mass of the trailer is 400, so 400 times the acceleration A. And so we get this equation, 2,400 take away R equals 400A. And so we get simultaneous equations, right? So if I state it down here, that's my first equation, and my second one is here. So I need to find A, the acceleration. Now I need to solve these simultaneous equations. You can solve them however you want. I would probably exercise some caution with just jumping right into your calculator's solver function right away without showing any working. It is 5 marks. I don't know. But it doesn't take much work to solve it manually. What I notice is I can eliminate R because I have minus three lots of R on the first one and minus 1 lots of R. If I just triple the second equation, multiply by 3, then I get 7,200. That's 2,400 times 3. Take away 3R is 1,200A. Now if I restate the first equation then, 7,400 take away 3R is 1,600A. How can I get rid of the 3R? How can I get rid of the R here? Well, I can take them away, right? Because then if I have minus 3R, take away minus 3R, that's a double negative. I essentially then add 3R. Minus 3R, add 3R goes to 0. So if I take these two away, so then I get minus 200, then 0 equals, well, 1,200A take away 1,600A is minus 400A. So then I get the equation minus 400A is minus 200. So if I solve for A, I get A divided by minus 400. Well, that's just a half. So A is 0.5 meters per second. So that is the A there. Okay, cool. Then it says in a refined model, the rope is modelled as having mass and the acceleration of the car to be A1. State how the value of A1 compares to the value of A. So A was 0.2, right? Now in this refined or adjusted or changed model, what's been changed is the rope is modelled as having mass. That causes the acceleration to be different. It's now A1. So what difference does the rope now having mass make? If it has mass, then if you think about it, the mass in the toe, in sort of the tow bar, right, the tow rope, it creates even more strain on the car. So the car's trying to move forward, right, but it has all this extra strain resisting it. If you just make the tow rope have mass, you impose even more strain on the car to move forward. So it's going to move slower, which means the acceleration will have to be lower. So I'm going to say as a result, A1 must be lower than A. Okay, and I don't need to say this, but I say it because as adding mass on the tow rope means the car has to overcome more resistance, hence it will move slower. And so there we are. Okay, but you just needed to say that because the question only said what was it, state how it compares. So is it lower, is it greater, or is it even equal to each other? Well, it's lower. Okay, then in part C, state one limitation of the model used for the resistance. So specifically, what's wrong with the resistance used here? So if we look at these two sentences to do with the resistance, it's modelled as a constant force. Modelled as a constant force here. That's the main issue. The issue is the resistance is constant throughout. So the resistance here and here, perhaps due to friction from the trailer and the car on the road, or the air resistance or whatever else, is it really going to be the same all throughout the whole journey? No. Again, if you might expect the heavier vehicles to have more resistance, and you might expect when the car is faster to again have more air resistance and more friction on the road. So it's inappropriate for the resistance to be constant all the way out. So the limitation is the model assumes resistance forces are constant throughout. In reality, they would vary depending on, for example, the speed of the car. So the faster the car, you expect more resistance, right? So that is the issue there.